All right. So this is an example eccentric loading columns, right? Here we are given a solid rod, solid column, right? And then these are some of the parameters of it: diameter, length, the load, which is the P here, the eccentricity, the distance between the central axis, and the line of action of the force P, right? And then the solid rod. Now we are being asked to find the maximum deflection, maximum stress in it, right? So this is what we're going to do. Given the parameters, we always know that for such questions or for such problems, the aim is to make sure that we are able to find these two easily, right? And one thing that helps our work is that you make sure you are using one particular unit. That way your works become much more easier, right? So looking at everything I have here, looking at the values, which is the diameter, length, force, and everything, you can see that the only thing changing is we have units, some units not being consistent. Like so, the unit of length, some are in meters, some are in mm, right? And then it depends on the problem. At times you want to find it in mm, but generally it's in mm because the deflections are not that much huge, right? So if we decide to do all this in mm, one important thing is to make sure you have a consistent unit. So the L is not in mm, so we convert that. We end up getting L being equal to, let's see, 2.5, and that gives us 0.0015 mm, right? And then the P2, there's some K attached, so we end up with 18 times 10 to the power 3 newtons. Eccentricity, that's 3, and that gives us 0.003 mm, right? One other thing is the elastic, sorry, what was that given? It's actually a GPA. The value given for the elastic modulus is 200 gigapascal, right? And this, one thing we know about this is that is stress over strain, right? So G here, first of all, we know that the E rather, we know the E to be 200 gigapascal, which is times 10 to the power 9 G, right? PE, sorry. We have the G to be the 10 to the power 9 already, Pascal, right? But then again, we know E to be equal to stress over strain, right? And anytime we are given E and then there's a Pascal, meaning that it's actually Newton per meter squared, right? So meaning that everything here is in meter, but we want that to be in mm. Another way is to go about it is that because this one is a bit confusing, you change everything to mm and then do the computation. When you are done, you convert to, you maintain everything in m, right? You change everything to m. When you're done, you convert back to mm, right? But if you want to change everything to mm straightforward and get to the answer straightforward, this is how you go about it. You know this E here, because of this Pascal, means that everything is in m already. So this is how we go about it. So this E here is 200, right? Times 10 to the power 9. This Pascal here means we have Newton per meter squared, right? But then if you want to change it to mm, if our plan at the moment is to change it to mm, this is how we go about it. This is what we do. So this will give us 200 times 10 to the power 9, right? The Newton is maintained. We introduce an mm here. So the milli comes in, right, which is 10 to the power minus 3, right? Minus 3, right? And then this is per, right? And then this moves with this m here, and all this is squared, right? And because we are introducing this, we are actually doing something to cancel it out. If it comes out, it becomes 10 to the power minus, this is actually 10 to the power minus 6, right? So what will cancel it is, I'm going step by step so we be able to see clearly what's happening, right? This means at the downside, to cancel just this 10 to the power minus 3, which is squared, we actually have to introduce a times 10. So this all at the down. So okay. So this here should be 10 to the power 6. Right. So it means that this 10 to the power 6 right here cancel this one with this, because this minus 3, 10 to the power minus 3 squared gives us 10 to the power 6, 10 to the power minus 6, which is cancelled by this, right? The same thing. But what happens is that because we want the maintained, right, we keep that 6 there, that this 10 to the power 6 there. So this will happen 200 times 10 to the power 9, right? And then this will change to squared, right? Squared. And this down here is 10 to the power 6, right? So if it moves up and joins this 10 here, it becomes 10 to the power minus 6, right? Newton per meter. Does it make sense? I'm sure it does. So what we get, we end up with this one is 10 to the power 200, right? Times 10 to the power 3 Newton per squared. So this is what we're having. So now that we have this, we can move on and solve the problem. So let's see what we need. We have the eccentricity in already. We know sec is reciprocal because our calculator doesn't support the sec. Reciprocal, of course, right? And then we, in this particular condition, the end conditions were given. So we just assume that everything has been done already. The effective length is the L that they've given us. So we just take this KL to be the length, right? The P is given, which we found in the basic unit. We have the E, we don't have the I. So now the only thing we need is the I, right? Okay, so the I is basically a cross-sectional property, right? And what was said about the question? We were told that it's actually a solid rod, and it's having a solid rod, meaning it's having a circular cross-section, right? So as such, it has a particular equation that describes the second moment of inertia, right? Which is this right here. The I, right? I is equal to pi r to the power 4. You see, you have the inside is darkened, so meaning the inside is darkened, meaning solid. It means solid cross section. It means solid cross section. Right? So now to find the I, this is the equation that we need. Right? So let's go about that. I is pi r to the power 4 on 4. Here we are given the diameter instead, which we say is 30 right? So let's see. There's pi, and then this is d, which is 30 on 2 to the power 4 on 4, right? So this will happen. So now let's see what we are getting for this. So we have pi times this right here, 30 on 2, and this to the power 4 on 4, right? And what does this give us? 39760. Point, let's see, 4 dp 7820, and this is actually in the unit of to the power 4, right? We'll go very shortly. This one here, this pi is a constant, there's a number, this having a unit of m, so if you square that m, it gives us to the power 4, right? So that's why it's the moment of inertia. The units are very important, very important. Without it, we don't know what we're talking about, right? So we have everything that we need. Our next thing, to make our work easier, because we don't have the sec, it will be much more convenient if we try to find the sec of all the cos, right? Or the cos reciprocal, right? So let's see. So we know that the sec of whatever that is there is actually, so first of all, let's rewrite the function, the equation rather. So this is a deflection equation, right? This is E, and then we have this, right? So this will mean 1 on cos of all of this, which is KL on 2 times square root of P on EI, right? All this, minus 1. So this is the same equation we written because we can't punch sec on our calculator. Right? So now let's do the cos inverse. So 1 on cos of what we're trying to find, right? We said the KL, because the end condition was specified, we consider the KL to just be just the length, right? So you have the length to be 0.0015, right, on 2 times square root of the P. I have the P to be 18 10 to the power 3. Right. And then our EI, our E, you have to be 200 10 to the power 3. And then our I is 39760, right? 0.7820, right? So this is all here. So this is what we're trying to find. So let's see. 1 on cos, right? Okay. Right. We have a fraction 0.0015 on 2, right, times another fraction times something else, which is the square root of 18 times 10 to the power 3, all on 200 times 10 to the power 3 times 39, right, 760 times, sorry, it's a point 0.7820, right? So let's see what I get for this. Again, whatever it is that we are doing here, because we are not doing angles, we use rad. So right, you see, I'm converting this dB here to rad. So now I have everything in rad. So let's see. Okay, so this is what I just punched. Very important. If it's not in rad, it's a whole new something that you are punching. Like the answer will be totally different. Right? So in rad, we are still getting 1. So let's see. A minute. Let's see if you're actually punching the right thing. 1 on this. 5 on 2. The length, let's see. Oh, here's the issue. The length is 1.5 m. So that 1.5, if we convert to mm, it will be a different value. So you see, unit conversion very important. If you choose a particular unit, be consistent with it. All right, so this should be 10 to the power 3, not minus 3. Right. So this is what we are getting. Okay. So we have this here to be 2.3357, right? So let's take the 1 away from it directly. So let's see answer. Right, so answer minus 1, and that's what it gives us. So let's see. So our deflection now will be E, Now we know the E to be in mm. That'll be 0. The E was actually in, let's see, the E was in mm, directly in mm. There was no need for us to do a conversion. So let's see, this E here was in mm. So there's no need for us to do any conversion. So this E here is maintained. Nothing happens to it. Same for this. So this actually should have been times 10 to the power 3 mm. 1.5 times 10 to the power 3 mm. Right. So the rest of the conversions have been done. Let's see. Our deflection, maximum deflection will be this. So we have E, we know it to be 3. And then because we subtracted, now we have this value. So if we take 1 from it, that will give us 1.3358, right? Approximately. When we do that, let's see. So this minus 1. So answer times 3. And this is what it gives us, because we convert, make sure that everything was in mm, right? We get 4.0073 mm, which is approximately about 4 mm, right? About 4 mm. Okay, so we have this. Okay, the next thing for us to do is to find the stress, the maximum stress. And then because the end condition have not been specified, we there's no need for us to even find the critical load and everything, right? So we use this first equation, right? We use this particular equation. So we're just going to copy that and use it. But the most important thing to know is that one good thing to know is that you get to notice that the first one, this one right here, is derived from this one. So if you don't have any of them, you can, even if you have the first one, you can just put in whatever it is you have available, and then you get the first one. But here, because the end conditions are not given, we are using this. Right. Okay. So now we are using this. So we go to the same process, put the equation down. We look at the values that we don't have. How do we get them? And then we move on to solve. Right. So let's see. So the maximum stress has the equation of this form. Let's see what we don't have. We have P, we don't have E, cross-sectional area. We have E, we don't have C, we don't have R. So we need this C, R, what again? Right, that's all. So we move on to find the A. The A is a cross-sectional area. Right. And we know this, the cross-sectional area of a circle to be what? Pi R squared, which is the same as pi d squared on 4, right? Is d squared on 4. So let's see what that gives us. So pi times 3 is actually 30. Everything in mm, and 4, and this gives us this. Let's see. Pi 30 squared on 4. So that gives us 706.8583 mm squared. And the unit here, very important. If you miss that, it's a whole new story, right? Mm squared. The next thing we need is the C, right? And then we know the C to be the distance from the central axis to the outermost fiber. When we look at the problem, right, it will be from here. We know that the diameter is actually was named 30, right? So basically the C will be half of the diameter, right, which is about 15. Is it so? Right, because we have the diameter to be 30 mm, right? So this C will be half of the diameter, right, which will give us about 15 mm. Yes. So our C we go to the D on 2, which is 30 on 2, and that gives us about 15, actually 15 mm, right? The next thing we need is the R. Okay, the R, the radius of gyration. There was a visual mistake in something we did earlier, but I corrected it with an overlay, right? So R is actually square root of I, right, which is the second moment of inertia, divided by the cross-sectional area, right? So that's how we go about it. We have the I, we have the A now, so the radius of gyration give us square root of them, their ratios. The A is 706.8583, everything in mm, and then the I, we had that to be 39760, right? 760 point, we're using 40p, right? 0.7820, right? 20. So let's see what we get for that. Square root is 39760 point 3976.787820 on 706.8583. What do we get for that? Get radius of gyration of 7.4999, yeah, mm, right? So this is our radius of gyration. This is the formula. We move on. Okay, anything else that we need? We have A, we have C, we have R. Now we just left with the computation. So let's see what we get for that. If I let's just point, because we have the equation here, we are going to point everything straight forward, right? So we have a P, which is about 1.8, right? Yeah, it's actually 18 times 10 to the power 3, right? And the area now we have to be 706, right? So 706.8583, and then we have the bracket inside. So we have here 1 plus, then again we still don't have our sec, so let's complete that first. It makes your work easier, right? It makes your work very easier when you do it that way. So let's see, let's copy this. So when you like look for the equation that you need, that's the first thing. The next thing is to check if the equation you are having or that you are using has everything that you need already, right? If it has everything you need already, then straightforward. If it doesn't, you look for the ones that you don't have, and the ones that are a bit complex for you, you find a way to simplify them and punch everything to make your work easier. So now we have everything except the sec, which we know to be inverse of cos, right? So we are going to get that. So that sec will be 1 on cos, right? And we'll put everything in. So that's the KL here. We said is the length, right? That gives us the L of let's see, yeah, what is it? Okay, 1.5 10 to the power 3, right? Because the end condition when specified, we take it to be the effective length to be just the L, right? So 1.5 times 10 to the power 3, and then 2R, we have an R now, which is 7.499 times 7.4999, right? And then we have our square root. Our P is about 18 times 10 to the power 3, right? Yeah, that's it. That's our P. Our EI, our E, we have that to be about 200, right? Times 10 to the power 3. Let's confirm. Yeah, 210 to the power 3. And then we have our I. What is here is 1. So let's put that. Okay. This multiplication dot. And our I is, was it 39,760,7820. Let's see if we can push that somewhere. 39,760.7820 or 780. That's why I add 7820. Yes, so that's it. So now we punch and see what we get for this particular sec. Right, so that's 1 on cos, right, bracket. It's always easier when using calculator aside to this particular calculator, right, to put in bracket to make your work safer, because if you miss a bracket to tell you that there's something missing. That's another way of safeguarding your answers or your procedure, right? And then we have 2 times 2. 2 times 7.4999 times the square root. Fraction is 18 times 10 power 3 on 200 times 10 power 3 times 39,760.7820. Right, so let's see. 39,760. So the maximum stress, now we have everything that we need. We're trying to find the cause, right? Okay, there's slight mistake that we made. This R shouldn't be here because of the particular equation that we choose, right? Very important. So most of the times it's important that you look at the equations given and then you just use what you are given, right? Not try to or the data you are given, right? So in this case there's no R, so if we try punching it, it gives us let's see, 2.3357, which is almost like the one we had earlier because the equations are the same. Yeah, that the cos sec side is the same, right? So that is what we get in the end when we take when we do this 1 plus E was 3, C was 15, and then R was about 7.4999. That's squared, right? And when we multiply by the answer that we had, that gives us that. So here we get our 18 times 10 to the power 3 on the area, which is 706,853.8583, right, in bracket 1 we point this already, we point what this right here, we point this. Yeah, so that's what's given us that, so we can just continue, and that will be times that, which is the 2.8687 approximately. So the answer right, so this times 18 times 10 to the power 3 on 706.8583, right, and that gives us the maximum stress of 73.0498, and because we did everything in mm, this will give us a megapascal, right? Megapascal. Yeah. All right.